Hi, welcome to the second video on convex sets. We'll begin with a class of theorems called the separation theorems. We'll prove them using the isolation theorems introduced in the previous video, first video. Then we'll look at extreme points of closed convex sets, compact convex sets, and we'll discuss an important theorem, the Crane-Milman theorem. Then we look at uh, convex cones. Uh, then we'll introduce an important convex cone called the positive semi-definite cone. And we look at some of its properties. Then we'll introduce inequalities, generalized inequalities under a cone. When we look at like some operations that preserve convexity. Finally, we look at dual cones and dual generalized inequality. So this will be the broad set of topics that are going to be covered in the second video. So separation theorems, they are theorems which provide certain conditions on sets under which you can separate them using hyperplanes. Okay. We'll first define what is meant to be separate to separate sets. So if A and B are sets in a vector, are sets in RD, then a hyperplane H is set to separate A and B. If they belong to different closed half spaces. That is, A could belong in H plus bar, or and B could belong in H minus bar. Or A could belong in H minus bar and B could belong in H plus bar. So for example, like if you look at two sets like this in R2, like you can readily separate them using this slide. But now we explore certain conditions under which convex sets can be separated. Before we go on to the first separation theorem, we'll introduce another definition. This definition is extremely similar to the definition of Minkowski sum that we are familiar with. So if A and B are sets in RD, then the difference between the sets A minus B is defined to be the set of all differences between sets. So this is the difference between the two sets A minus B. Associated, we have this proposition. If A and B are convex sets. Then A minus B is also convex. So the proof is very simple. We'll prove this result when we introduce operations that preserve convexity. So here is our first separation theorem. So this is the most general separation theorem. This does not involve an explicit construction. So later we'll relax some of these conditions where such that we can actually explicitly calculate some hyperplanes. So let A comma B be non-empty convex sets in RD. Then there exists a hyperplane H such that it separates in we'll now prove this. So here it's mentioned that A and B are both convex. Then the Minkowski difference is also convex. So here I left an important condition, that is A and B be two non-empty convex sets, and A intersection B is null. That is, they don't intersect. So A minus B is also convex, and since A intersection B is null, 0 not element of A minus B. Then by our specialized isolation theorem that is proved for Euclidean space, there exists hyperplane H which contains 0 and isolates A minus B. The existence of a hyperplane X means that there exists a linear functional f such that f of z is greater than or equal to 0 for all z element of A minus B. So this is from the definition of hyperplane. By hyperplane we mean a set where some linear functional f is a constant. Since the hyperplane passes through 0, that constant has to be 0. This implies that f of x minus y greater than or equal to 0 for all x element of A and for all y element of B. So this means that f of x greater than or equal to f of y for all x element of A and for all y element of B. This means that if you choose, say, alpha to be maximum value of, say, y element of B, f of y, then f of x is greater than or equal to alpha and f of y is less than or equal to alpha. Here for all x element of A and for all y element of B. This implies that the hyperplane H tilde given by x such that f of x equal to alpha separates A and B. Thus, we are done with our theorem. We'll now introduce a different version of the isolation theorem. Suppose A is a closed convex set. Notice this closed in Rd and U in art element of A. Then there exists a hyperplane S which strictly separates notice this strictly A and U. So this is a separation theorem classified as a separation theorem, but it's similar to isolation theorem. Come to the proof. Our first statement is that D of U A is strictly greater than 0. By distance between a point and a set, we mean suppose not. We prove this by contradiction. Suppose not. Suppose that D of UA is indeed 0. This means that 1 by n is not an infimum of this distance. This implies there exists xn element of A such that mod xn minus u is less than 1 by n. What you have is a sequence of points xn such that mod xn minus u to sequence in A converges to 0. You can show that this xn is a Cauchy sequence in A. Which implies xn converges. In fact, you can show that xn has a convergent subsequence. That would be easier using the Bolzano-Weierstrass theorem. So what matters is that you have a point x star, which is some limit n tends to infinity xk, some subsequence. But this set A is closed, which implies x star element of A, but the limit of this distance between x star and u is 0. This implies u element of A, which is not possible because we have assumed that u is not in A. Then so let epsilon be the distance between u and the let epsilon be this d of ua, which is a strictly positive quantity. Then if you choose a ball of radius epsilon by 3 at u, and you add the epsilon by 3 to A, by this you mean so you are adding an open cover, like you are increasing the range of A by this epsilon by 3. So what you end up with is two open sets which do not intersect because of this condition. So what you end up with are this open ball at U and some open set A plus epsilon by 3, which do not intersect. By our first proved separation theorem, there exists a hyperplane H which separates these two open sets. Then, but separating two open sets means that they are strictly separated. So automatically, H strictly separates N. Separates these two open sets. So if you want more explanation, you can find them regarding the statement. You can find them in my written notes. So I provide one more example of what this adding this epsilon by 3 ball to the set A means. So if you are in R2 and your set was this line, and suppose you added a ball of radius 1. So your set is this A, and you added this 1. What it becomes is you are adding these balls to all points. This you finally end up with a cylinder like thing. These were the original endpoints. So this is what you end up making. So this is just an explanation for what this adding epsilon by 3 to a set means. So we have finally proved our second separation theorem. We now prove the same separation theorem between a point and a closed convex set, but this time we'll provide an explicit construction. So this theorem will be much more instructive in that it helps us understand more properties of how to separate a point and a convex set. So then there exists a point V element of A such that mod U minus V, that is the distance between the set points U and V, is less than or equal to furthermore, the hyperplane H passing through U plus V by 2 and normal to U minus V strictly separates U and A. So for example, if this is U and you had some closed convex set here, it need not be bounded, but here for explanation purpose I'm using a bounded example of A. So the point, we have to find the point closest to U. So this will be a point, say, closest to U. Then your hyperplane will be this. It's passing through the midpoint and it's perpendicular to U minus V. So we'll now set to prove this thing. We will first show that show the existence of this point V. So to show that, we'll first define this V star to be infimum X element of A. So already in the earlier separation theorem, we proved that D star has to be strictly positive. It cannot be zero. So then we follow the same approach. So D star plus 1 by n is not an infimum. This implies there exists and one by xn such that mod u minus xn is less than d star plus 1 by. So again, we have a sequence xn which converges in norm to this d star. That mod xn minus u 2 tends to d star as n tends to. Now we need to show that xn has a convergent subsequence in A. To do that, so we notice that for n equal to 1, if you look at a ball of radius d star plus 1 at u, plus for safety we'll take d star plus 2, the closed ball of radius d star plus 2 at u, it must contain all the xn's because the distance between x1 and u is less than d star plus 1. So it must all be contained in this closed ball. But now see that this closed ball is a compact set. It's closed and bounded. Thus, all these sequences are contained in a closed and bounded compact set. So by the Bolzano-Weierstrass theorem, there exists a convergent subsequence. There exists some subsequence which converges to some x star, but A is closed, therefore x star element of A. So we'll call this x star as RU, as RB. Sorry. So we have already proved the existence of this. I would like to add that there is an addition to the theorem. There exists a unique point. So we have already shown the existence. Now we'll show the uniqueness. The uniqueness follows from convexity. So suppose there existed V1 and V2 with the property that they were the closest point from U to A. Then if you look at this triangle formed by U, V1 and V2. So this is an isosceles triangle because by assumption both are value d star. Then if you look at the perpendicular bisector of this line connecting V1 and V2, because it's isosceles, this angle is right angle. This means that, and this point is V1 plus V2 by 2, the midpoint. This means that mod U minus whole square plus mod V1 minus V2 by 2 the whole square. This mod U minus V the whole square. By the Pythagoras theorem. This means that this distance between U and the midpoint is smaller than d star. So we have a contradiction. So thus we have finally proved that there exists a unique point. Uniqueness followed from the convexity part. And the existence followed from the fact that A was closed. So we are done with our first half of the theorem. So there's one more comment. This point V, the unique point, it's usually called the projection of U onto the closed convex set. We also have this interesting property of the projection. using which we'll prove the existence of a hyperplane. So the property is this: if V is the projection of U onto A, which is a closed convex set, then uh, U minus V, X minus V is less than 2 for all X element of A. So this is very easy to visualize. So if you have this point U and you have this convex set, closed convex set, this will be your point V, which is closest to U. And now if you choose any point X, so this will be V minus U and this will be X minus V. You can see that they always make a angle more than 90 degrees. Therefore, the cos of the angle between them is negative. That is essentially what this theorem is saying. We'll prove this in the following way. Consider this function g of t, which is mod u minus tx plus 1 minus t v. Now notice that when t equal to 0, g of t is the distance between u and v. Because it's the minimum of any distance between x and the set a and u, even if you move a little, for even extremely small t, if you move a little t forward along x, g of t must decrease. So we'll make use of this property. So we'll expand g of t. We can continue to expand this. You write this norm square as in terms of inner product. And we'll collect the first order terms in C. So that will be u minus 2 plus plus order t square. This is mod u minus v the whole square minus 2t into u minus v x minus v. We'll change the sign. Oh, so we don't. We don't need to change the sign. So basically, uh, because g of t has a minimum at t equal to 0, for an extremely small movement t along the x direction, this quantity has to increase. So we are neglecting the order t square term. Because this is negative, this in turn means that has to be less than 0. So we are done with our proof of this particular property. We now use this to prove the existence of a hyperplane. We now define our hyperplane X to be a set of all x such that uh, so we'll determine this constant alpha from the condition that it has to pass through the midpoint between u and v. So u plus v by 2. This means that alpha must be equal to u plus v by 2 comma u minus v. This means that it must be equal to half mod u square minus mod v square. So we'll first, we want to show that this hyperplane strictly separates u and the set A. So this can be easily proved. So let us check the value of f at hyperplane. We'll call this the functional f at u. So this will be u minus v, and the value at v is, so the difference is a strictly positive quantity because u does not lie in A. Strictly positive. This implies that f of u is strictly greater than f of v. Now, because f of x minus v is less than 0, just this is exactly the property that we proved, but now written in terms of this function. This implies that f of x is less than f of v. This implies that f of x is less than f of u for all a. This means that h strictly separates u and the set A. So we are done with the proof. While this proof was kind of extremely big, we got to know several interesting properties of closed convex set. First of all, that if you are given a point u that is not in the closed convex set A, then there exists a unique projection of u onto A. Furthermore, we had this very interesting property that u minus v, x minus v is less than 0 for all x elements of A when v is the projection. So these kind of properties will be useful later on when we go to proving things like gradient descent. We'll now state another separation theorem. However, the proof is extremely simple because we have already done all the heavy lifting in the proof of the earlier theorem. The statement is this. Let a comma b be furthermore assume that b is compact and A is closed. Then there exists points u element of B and B element of A such that mod u minus V is less than or equal to mod x minus y for all x element of A and y element of B. Furthermore, the hyperplane H passing through u plus v by 2 and perpendicular to the direction u minus v strictly separates A and B. So we'll first show the existence of u. So define a function f from b to r positive, where f of x is defined to be the distance between x and the set A. Now, because B is compact, f assumes a minimum. I mean, in B, that means that there exists this u element of B such that it's the minimum value of the function on B. So we already have a distinguished point u element of B, and we have this closed set A. Now we just assume, apply our earlier separation theorem between point U and a closed convex set A. We already know get the existence of this point B. It's already proved. Then, as usual, we have this using that special property of projection. We can show that the hyperplane passing through the midpoint separates U and A, and so we are essentially done. So the only thing to do in this whole theorem was to show the existence of this U, which is shown because the set B is compact, and as you know, any function from a compact set to real numbers assumes both its maximum and its minimum in the set. We'll now come to extreme points and extreme points of a set, and we'll discuss one very interesting and important theorem called the Crane-Millman theorem. So we'll first define extreme points. Let V be a vector space and A is subset of V. Then U element of A is called an extreme point. Of A if the only way to have U equal to A plus B by 2 for A comma B element of A is that A and B are both equal to U. For example, if you have a pointed set with a pointed structure like this, then this will be an extreme point because there's no way to write take two other points in the set and write this U as its midpoint. The set of all extreme points of A is denoted by X, this symbol. We will now define a useful theorem connecting extreme points to functions. Let V be vector space. A contained in B is non-empty, and f is a linear function. Then, so first, if the set of all points where f takes a maximum or a minimum, let's proceed with this maximum, is in fact unique. This contains one point. Then that point is an extreme point. If on the other hand, there are multiple points, then an extreme point of B is an extreme point of A. The proof is very straightforward. For the case of 1, if the point is unique, then if u is written as a plus b by 2, then f of u will be f of a plus f of b by 2, because f is a linear function. But since f of u is maximum, this implies that f of a, the only way is for f of a and f of b to be equal to f of u. But since the point where it takes maximum is unique, this implies that a has to be equal to b, has to be equal to u. Secondly, suppose b is the set where f takes its maximum. Then now again, suppose you pick an extreme point of B, then in particular we want to show that if u is written as a plus b by 2, where a comma b lies in A, then a and b are both equal to u. Now again you write f of u as f of a plus f of b by 2. For the same reason, because f of u is maximum, there's no choice but f of a and f of b be equal to f of u. But this implies that a comma b lies in B, but u is an extreme point of B, and a and b lies in B. This means that by the definition of extreme point, u is a equal to b. So we are done. We'll now prove a simple consequence of our earlier theorem. Suppose K is a closed convex set, and F is the face of K. Then an extreme point of F is an extreme point of K. So the proof is simple because F is a face of K. There exists a hyperplane H which isolates K, and such that F is H intersection K. Now H isolates K means that f of x, where f is the linear functional which defines the hyperplane H, f of x is less than or equal to alpha for all x element of K, and f is the only place where x f is the only place in K where f of x is equal to alpha. This means that the set B of the earlier theorem, the set where a linear functional takes its maximum is the face F, and thus by our part 2 of our earlier theorem, any extreme point of F is an extreme point of P. We will now state and prove the very interesting Crane-Millman theorem. Let K subset of RD be a compact convex set. Then K is the convex hull of its extreme points. So this is very interesting. We will prove this by induction on the dimension of the Euclidean space RD. So first, for d equal to 0, the statement is trivial because it's just a point. Now let us assume by induction hypothesis that the statement is true for all dimension less than d. Now we'll check at the dimension d. We can, without loss of generality, we can assume that K has a non-empty interior. This is because if K had an empty interior, then we had already proved a theorem in our first video that you could always go to a affine subspace of strictly lower dimension where K has an empty interior. Then by our induction hypothesis, since the statement is true for all dimension less than d, we are done with this case of empty interior. Now we'll consider two cases. Case 1, U lies in the boundary of K. Then by a support hyperplane theorem, there exists a hyperplane H such that U element of H and H intersection K is a phase F, and H isolates K. This means that U element of F. Now, because K is a compact convex set and the phase F is a closed subset of a compact set, F itself is compact. This means that by our induction hypothesis, U can be written as a convex combination of extreme points of F, because F has strictly lower dimension than K, because F is a hyperplane, intersection of K with a hyperplane of lower dimension. Um, and as we proved in our earlier theorem, extreme points of the face is an extreme point of the set itself. So U element of convex hull of extreme points of K. Now, thus we are done for the case when U lies in the boundary. Now, for the case when U lies in the interior, we'll prove this part by very easily looking at a diagram. Suppose this is K, a compact convex set, and this is your U, which lies in the interior. Consider any line passing through U. Then L intersecting K must be a interval, and its endpoints must lie on the boundary, as you can easily see from this figure. L intersection K is an interval, and this interval A comma B is such that A and B both lie in del K, the boundary. This is very easy to see. This means in particular that U can be written as a convex combination of A and B. And in particular, A and B, since both lie in the boundary, from the first case, they can indeed be written as a convex combination of extreme points of K. So we are done. Another comment is that this particular example itself is enough to show the illustrate this Crane-Millman theorem. So the extreme points of this hexagon are exactly these darkened points, and one can easily verify that this hexagon is indeed the convex combination of these vertices, which are the extreme points. We now come to the topic of convex cones. So we first define cone. Uh, so basically, a cone contains the origin and any ray. For example, cone could be just these two rays, but we are interested in convex cone. So convex cone means it's a cone with which is convex. So we can combine both the definition of cone and convexity to arrive at the following definition. So this would be the definition of a convex cone. For example, because of convexity, this convex cone must contain all the rays in between these endpoint rays. We now have the definition of conic combination. So given x1 etc. up to xn contained in RD, uh, conic combination of these points is a point of the form alpha 1 x1 plus etc. alpha n xn where all the alpha i's are greater than or equal to. So there is no constraint of them summing up to 1, as in the case of convex combination. We also have the usual definition of conic Hull. So given a set S, the conic hull of S, denoted by the symbol, is the smallest convex cone to contain S. Uh, yeah, or it can be defined as the set of all uh, conic combinations of points from S. So these definitions are extremely similar to those of a convex hull, affine hull, etc. As an example of a convex cone, consider the norm cone. Suppose this is any norm in RD. Uh, the norm cone is defined as the set of is a subset of RD plus 1, such that say, for example, if this was the standard Euclidean norm, then you would have the standard cone which you imagine in R3. So each at this is the t axis. So at each t equal to t naught, this cross section will be a circle of radius t naught. We now define what is called a proper cone. So if one k is closed, uh, 2k has a non-empty interior. Three k is convex, and 4k is pointed. By pointed we mean if it does not contain any whole straight line, or equivalently we can write if both x and minus x lie in k, this means that x is 0. We can use a proper code to define what are called generalized inequalities. So we'll come to the reason why all these properties for the proper cone are required when we explore properties of these generalized inequalities. So, but we say that x is less than or equal to y with respect to k when y minus x lies in k, and there's a strict inequality. X is strictly less than y with respect to k when y minus x lies in interior of k. So this is the reason why we wanted a non-empty integer to define the strict inequality. Uh, we can relate this to the normal inequality that we know of in R. So this happens when you choose the cone k equal to R plus in R. Then the generalized inequality with respect to this R plus in R becomes the standard inequality. But we could also have other inequalities. Say in Rn, we could choose k equal to the positive orthen Rn plus. Then we would have this only if all the coordinates of y are greater than x, that of x. So note that in Rn, there's this interesting property that not all elements are comparable. For example, if some coordinates of y are greater than that of x and some components of y are less than x, then they are not comparable. However, in R, there's this property that all elements x and y are comparable. Either x less than or equal to y or y less than or equal to x. This property is not satisfied for other generalized inequality. We will now look at some of the properties of generalized inequality. First one, it is preserved under addition. For example, if x is less than or equal to y with respect to k and u is less than or equal to say w with respect to k, then x plus u is less than or equal to y equals w. So this property is true because a cone is closed under a non-negative combination. This is the conic property. Second property is that it is transitive. This means that if x is less than or equal to y and y is less than or equal to z, then x is less than or equal to z. Again, this is because of the closure of like the cone being closed under non-negative linear combination. Because z minus x, you can write it as z minus y plus y minus z. If both lie in k, then their sum must also lie in k. So another property is that the inequality is reflexive. This means that x is comparable to x. This is because we have the property that 0 lies in the cone. Next, we have the anti-symmetric property. So if x is less than y and y is less than x, implies x equal to y. So this property is because of the cone k being pointed. And next we have closure under limit. So if xn is less than or equal to yn for all n, element of natural number, then limit n xn is less than or equal to limit n y. This is because K is a closed set. It that means it contains all its limit points. We now come to a very important example of a cone, called the positive semi-definite cone. So before we go into the details, we introduce some basic linear algebra conventions and definitions. So the first definition of a symmetric matrix and n cross n matrix is said to be symmetric. Matrix A, whose components are Aij, is said to be symmetric when Aij is Aji for all I comma j. So uh, we call the set of all symmetric matrices with this symbol Sn is the set of all symmetric n cross n matrices. Uh, so if you notice, to describe a symmetric matrix, we need to describe only need to describe what happens on the diagonal and on the upper diagonal, upper triangular part. So the strictly lower triangular part is completely determined by its symmetric counterpart. So we essentially need only n into n plus 1 by 2 elements to describe a symmetric matrix. Thus, we associate this set of all symmetric matrices with RD, where D is n into n plus 1 by. So this is the dimension of the set of all symmetric n cross n matrix. Now, if you have any orthogonal matrix, matrix U, by orthogonal we mean U transpose is U inverse, and a symmetric n cross n matrix, then U transpose A U or U inverse A U is also symmetric. Now, from the spectral theorem of linear algebra, so one can check that in any linear algebra textbook. We know that if A is a symmetric n cross n matrix, there exists an orthogonal transformation. O such that O transpose AO is a diagonal matrix. So this is called the diagonalization of the symmetric matrix. But the special property of symmetric matrices is that it can be diagonalized by orthogonal transformation. We now define the inner product in the space of all symmetric matrices. So if A and B are symmetric matrices, then A dot B is defined as trace of AB. So this is going to be a inner product. One can show that it satisfies all the properties. So when written in terms of components, this will be sum over ij, A ij, B ij. Now from the cyclic property of trace, one can show that uh, U U transpose A U transpose B is AB. So one just needs to apply the cyclic property of trace and the orthogonality property of U. Associated with every vector, X in RD. So there exists this symmetric matrix uh, that is XX transpose. So it's also written as X tensor product X. So the components of this matrix are Xi, Xj. One can indeed show that this is a matrix of rank 1 associated with every symmetric matrix A. Uh, there exists a quadratic form QA from RD to R, where QA of X is X transpose AX, or in fact, this is sum over Ij, Aij, Xi, Xj. So using our notation of this X tensor product X, one can write this as sum over Ij, Aij. So this is simply A. We finally come to the definition of positive semi-definite and positive definite. So an n cross n symmetric matrix A is said to be one positive semi-definite if QA of X, the quadratic form, that is X transpose A, is greater than or equal to 0 for all X greater than 0, and it's positive definite if the only way this QA of X is 0 is when X equal to 0. So one can also look at this properties based on the eigenvalue decomposition of these matrices. So positive semi-definite means all the eigenvalues are greater than or equal to 0, and positive definite means the eigenvalues are strictly greater than 0. We call the set of all positive semi-definite matrices are denoted by Sn plus, and positive definite are denoted by Sn plus plus. So we now show that the positive semi-definite cone is a proper cone. Uh, So in order to prove this, we need to prove three statements. One, first of all, Sn plus is a convex cone. So this can be proved easily. Suppose A comma B were elements of Sn plus, and if you look at any alpha beta greater than or equal to 0, then we just need to show that alpha A plus beta B is also in the convex cone Sn plus. So in order to show that, we look at this condition for a symmetric matrix for being positive semi-definite. So X transpose alpha A plus beta B X can be written as so since both A and B are positive semi-definite, they are both greater than or equal to 0. Hence, this whole quantity is greater than or equal to 0. And since X was arbitrary, this is true for all X. So the conic combination of A and B are also is also contained in the positive semi-definite cone. Second, we proved that Sn plus is closed. So to show that, consider this QA of X, which was nothing but A. Now fix an X. Let's call this QX of A. Different notation for the same thing. If you fix an X, then this QX of A is a map from Sn to R. So basically, you are claiming that this quantity has to be greater than or equal to 0 for all X greater than or equal to 0. Therefore, what you're looking at is QX inverse of 0 to infinity intersection X. So I'll explain. So this Q is a continuous map, and this is a closed set. This means that inverse image of, because Q is continuous, inverse image of a closed set is closed. So this whole set is a closed set, and arbitrary intersection of closed sets are closed. So you have that this whole set is closed. Now this whole set means that it's a set of all matrices where QX of A is positive. Thus, in fact, this is the set of positive semi-definite matrices. So you are essentially shown that Sn plus is closed. So third is the property that K is pointed. I mean, Sn plus is pointed. So this is very simple. So if X and minus X both are lying the positive semi-definite cone, if you look at the minus eigenvalues of both X and minus X, there will be negatives of each other. So essentially, you are saying that both lambda greater than 0 and minus lambda greater than 0. So this implies all the lambdas are 0. So X has to be 0. So the only set with both the antipodal pair contained in Sn plus is the 0 matrix. We have one more property left to prove that the positive semi-definite cone is a proper cone. That is, Sn plus has a non-empty interior. So we claim that the interior of Sn plus is nothing but a positive definite matrices Sn plus plus. So in order to show this, let us pick any A in Sn plus plus. We have to show that there exists an open set O such that A is contained in O and O is in turn contained in Sn plus. So this is the definition of being open. Uh, so when we discuss the norm balls, we discuss this particular characterization of a norm ball. So a ball of radius epsilon centered at A is the set of all A plus epsilon uh, some U. Okay, maybe I use bad notation. Uh, Plus some sigma such that mod sigma is 1. So this is the definition of a ball centered at A of radius epsilon, open ball. Now what we have to show is, sorry, mod is less than 1. So this is an open ball. What we have to show is that for some choice of epsilon, this ball is contained in this cone of symmetric positive semi-elliptic matrices. So we first look at the implication of this sigma matrix having a norm less than 1. So norm sigma square is less than 1, which implies that the inner product is less than 1. And we had already mentioned that the inner product is the trace of the two matrices. Thus, trace of sigma square is less than 1. Or sum over ij sigma square ij is less than 1. Though, so this in particular implies that mod sigma ij is less than 1 for all ij. Like if the sum of squares of some numbers are less than 1, then each of the entry has to be necessarily less than 1 in model. Now, in order to show that all elements of this open ball lie in Sn plus, we look at X transpose A plus epsilon. So this is X transpose AX plus epsilon X transpose sigma X. Now let us look at this term X transpose sigma X. This will be sum over ij xi xj sigma ij. So in particular, the modulus of X transpose sigma X must be less than or equal to mod xi xj mod sigma ij. So we now use this property that mod sigma ij must be less than 1. So you will get that this is less than or equal to sum over ij mod xi xj. So this is some bounded quantity because it's a sum over finite quantities. Let us call this quantity capital M. So the modulus of this quantity is at most capital M. And we have to check that, so the worst case scenario is when this happens to be minus epsilon M. So we just need to choose epsilon such that this quantity is never negative. So if X is the eigenvalue, X is the eigenvector, corresponding to the smallest eigenvalue of A, then X transpose X is simply lambda mu. The normalized eigenvector. Then all you need to ensure is that for this X transpose A plus epsilon sigma X is lambda min plus minus epsilon b. So if you choose epsilon to be lambda min by 10b when we are done. So this quantity is never negative. So for b of a, uh, lambda min by 10b, this must be contained in Sn plus. So we have just shown that the interior of Sn plus is nothing but Sn plus 2. So a comment about our earlier proposition relating positive semi-definite cone as a proper cone. So this enables us to, in fact, define generalized inequalities, matrix inequalities, using positive semi-definite matrices as the proper cone. So we now go on to defining minimum and minimal elements using a proper code. So first we have the definition. So if you have a set S, then Y element of S is called a minimum if X minimum with respect to some generalized inequality K with some proper code K, if X less than or equal to Y for all X element of S. So in particular, this means that, for example, if you are in some R2, and this is your Y, this means, and your cone is something like this. The set S has to lie within this cone for Y to be the minimum element. If, for example, Y was such that this is Y and say this is your cone, the set S when beyond the cone K, then Y would no longer be the minimum element. And associated definition is that of minimal element. So for a set, Y element of S is called a minimal element. If X less than or equal to Y happens only if X equal to Y. So in order to visualize this, again you could have some set S, and what this means that there is no element that is less than or equal to, if this is your cone K, the negative cone K, there's no element that is less than or equal to, there's no element X element of S which is less than or equal to Y. So a minimal element need not be a minimum element. So like if you have a set S like this, then this is a this point would be a say with respect to this cone, your cone in R2, standard cone in R2, then this point would be a minimal element, but it won't be a minimum element. Whereas this point is both minimal and minimum. We now define what is called a dual cone. So if you have a cone K, then the dual of K, called written as K star, is the set of all Y such that it's a set of all Y which makes a positive angle with all the elements of the cone K. For example, the positive orthant Rn plus is its own dual. And another example is the positive semi-definite matrices Sn plus is also self-dual. So one can show this quite easily. So I'm not writing the proof here for want of time. One can check the proof either in Boyd or the book by Boyd or my written notes. We now describe some properties of dual cone. So K star is convex and closed. So this is true even when K is not convex. If K1 is contained in K2, then K2 dual of K2 is contained in dual of K1. If K has a non-empty interior, this implies K star is pointed. So if closure of K is pointed, this implies K star has a non-empty interior. If K is closed, then the dual of the dual is the cone itself. So all these properties one can verify, but what they essentially imply is that if you have a proper cone, then the dual is also a proper cone, which in turn means that if you have some generalized inequality defined with some proper cone K, you can have a dual description of the generalized inequality using the dual cone K star. So we'll end this video by quickly discussing some operations that preserve convexity. So suppose first one is intersection. So suppose you have all the Ki that are convex, then intersection I Ki is convex. So this is because if x comma y element of intersection I Ki, then x comma y element of Ki for all I, then theta x plus 1 minus theta y element of Ki for all I for all theta in 0 to 1. This means that this convex combination lies in intersection I Ki. So the intersection of convex sets are all. The second is the Minkowski sum of two convex sets is convex. So if A and B are two sets, then A plus B is defined as the set of all x plus y such that x element of A and y element of B. Now if you take some z1, z2 that lies in A plus B, this implies there exists x1, x2 element of A and y1, y2 element of B such that z1 is x1 plus y1 and z2 is x2 plus y2. Now if you take any convex combination theta z1 plus 1 minus theta z2, then this is simply seen to be the convex combination theta x1 plus 1 minus theta x2 plus theta y1 plus 1 minus theta y2. So because A and B are convex, each of the entry inside the curly braces, they are both one of them is element of A and the other is element of B. Hence, this is also part of the Minkowski sum. So this element of A plus B. So the Minkowski sum is convex, provided A and B are convex. So another important thing is image under affine functions. So if f from Rm to Rn is called an affine function if it is of the form of a linear function plus a constant. So you can represent f of x as ax plus b, where b element of Rn and a element of Rn cross n. So one can very easily check that if one is S subset of Rm is convex, then f of S is convex. And if T subset of Rn is convex, then F inverse of T is convex. So one can use this to show several other the convexity of other sets. For example, a convex set under translation or convex set under scaling all comes under this class of affine functions. So due to lack of time, I am stopping here. But there is one topic that has not been covered. That is the transformation of convex sets under linear fractional functions and perspective functions. This can be referred from the book Boyd.